Hi, we are the Ostentatious Octopi, and this is our final proposal. For this project, we will be studying the flying squirrel. This project centers around developing an innovative design by drawing inspiration from the unique aerodynamic and gliding capabilities of the flying squirrel. The project aims to translate key biological principles to enhancing aerial mobility and efficiency in robotics. To do this, we will mimic the gliding capabilities of flying squirrels. We will attach large wings and a stabilizer, which will enable limited control of flight path when falling. We will also integrate servos for wing deployment, allowing for extension and retraction. We will also be mimicking crawling and leaping. This will be done through motors and a spring system to initiate the glide and traverse the landing area. And we will also have a lightweight body done through light and strong materials to prevent failure when crashing and maximize the drag on body. We will also be reinforcing the electronics against repeated impacts through testing. The primary hypothesis being tested is that integrating key features of the flying squirrel's aerodynamic design and glide behavior into a robotic system can significantly improve its gliding stability, takeoff and landing capabilities, and adaptability in dynamic environments. Our novel biological principle is the efficient aerial locomotion of the flying squirrel. This is done through them seamlessly transitioning between powered flight and controlled gliding. We will be studying two main things, the aerodynamic shape and membrane structure, along with gliding kinematics and energy efficiency.
To start with this project, we did a discovery decomposition on a paper analyzing the 3D kinematics of the gliding performance of flying squirrels. It started off with a background and hypothesis noting that gliding is a simple form of flight, but also that little is known about gliding in animals, while also noting that mammalian gliders have a low aspect ratio wing that's mostly rectangular that connects from the wrist to the ankle. The methods to do this study were that they glued small spherical reflectors to specific areas on the squirrels, put them on launching platforms with a landing pole a specific distance away, and then measured their flight using two high-speed cameras at two different distances to measure the 3D position of the squirrels. The results of this study were that they noted a high correlation between the gliding pitch angle and limb movement of the squirrels. They also noted unexpectedly that the drag coefficient didn't actually change with gliding distance. Also that each squirrel had a very high wing attack angle throughout the glide, as well as that the glide path started with a steep glide angle and then it leveled off before landing. Some conclusions that were able to be drawn from this study were that these squirrels were actively controlling their glide angle for stability, when analyzing these glide paths using classical aerodynamics, they expected the stall in these slow conditions, but when analyzing the path, they found that the squirrel started off with a steep glide that built up enough speed to generate the appropriate lift and the glide angle stabilized. And putting those two together, they found that using this flexible wing membrane, the fur and the low aspect ratio wings, gliding was allowed with these conditions. So the test hypothesis that was confirmed was that 3D kinematic analysis was useful in analyzing the aerodynamic gliding performance. Doing an analogy check on the squirrel versus our gliding robot, there's a lot of similarities. We were able to find that both were using membranes for gliding and that both are planning on using limb adjustment for gliding stability. Structurally, the squirrel is quadrupedal. We're planning on basing our robot on hexapod design, so it's slightly similar. Skin membrane is connecting fore and hind for squirrels, whereas ours is going to be a dedicated deployable surface. Size, both are very similar, as are the operating environments of crowded forests, although squirrels will be gliding from tree to tree, whereas ours is planning on just gliding from the ledge to the ground. Functionally, both are similar. The limb placement affects the membrane. Characteristics and specifications are also very similar, except that for squirrels, they also must climb to the necessary height for the launch, whereas our plan is just to walk it to the cliff and then glide from there. Performance criteria are also equally similar and dissimilar, where squirrels must climb and appraise the landing area, whereas we're just taking off, whereas both of us need to successfully glide to our target. As for constraints, they're mostly dissimilar. For squirrels, the wing membrane serves as the skin, where ours is a dedicated airfoil. Aging is not an impact for us, but for injuries, we need to make note of the potential for impacts breaking our robot.
Okay, the experimental methods that we're using in testing that we're using on this robot, we'll first look at the structural strength, how it holds up with walking, and then how it holds up for drop tests. And takeoff and leaping will be a spring actuated system. We'll record the height and the distance that the leaps achieve. And then we'll look at flight tests. We will look at the wing deployment, how long it takes and how efficient it is. And then we'll record flight and observe the stability and distance it travels. So the data that we need to validate our hypothesis is, can the robot perform a leap-off jump with jump height, jump length? Do the modifications allow our robot to glide, the flight distance, the flight duration? Is the robot stable while gliding? This will be changed. We can alter its tail as well and this will just be observed data. And then can the robot land? This will also be observed data on landing orientation and then inspect for any damage to the joints or electronics. The anticipated results from this performance is that we'll still have a robot that can walk, that can deploy external extremities for gliding. It can perform a launch procedure. It shows gliding capabilities that are stable. It maintains stable flight with no pitching or rolling, and it survives repeated landing without any significant damage. The significance of this robot is to build a robot that is capable of forward progress when encountering drop-offs that would otherwise limit a walking robot.